Welcome to section 5.3, solving trig equations, and I believe this is our last section of notes for this portion of chapter 5. So, I've already gone ahead, I believe, and done, yes I did. I did 2 other examples in the notes, just written out pretty basic, just to try to get us started on this, and I thought we would continue on with some stuff that's a little bit more complicated. So here we've got our first problem for the video lesson. 2 sine x cosine x is equal to root 3 sine x. So when we're solving trig equations, it's a little bit different than trig proofs. In trig proofs, we only want to deal with one side of the equation at a time to try to get it to match the other side. However, when you're doing trig equations, you want to try to get x equals out of this. So we do need to do a little bit more algebra with the whole shuffling back and forth across the equal sign. So I like doing this type of a problem because a lot of students see the idea of dividing by sine x and think that's brilliant. Well, I'm here to tell you you don't want to do that. If we divide by sine x at this point, there's a possibility that you're dividing by 0 or you're eliminating a solution, and that's no good. So although these two guys are on opposite sides of the equal sign, I want to pull them together because if it looks like you can divide by trig and knock something out, what you want to do is actually get them on the same side, set equal to 0, and factor. So let's move this guy to the other side and then try factoring. So your tools from Algebra 1 really come into play in this section, and from Algebra 2 a little bit, more so from Algebra 1. So I have moved it over so I have this whole equals 0 thing, which hopefully is triggering in everybody's brain, the whole zero product property. And I want to factor because I see that both of these have that sine x in common. So let's go ahead and factor out that sine x and see what happens. So they each have a sine x. Let's pull that out. And that gives me a 2 cosine x minus root 3 is equal to 0. So I know I see trig, which tells me that I'm definitely not in an Algebra 1 course, but on the other hand, I see multiplication and 2 things being equal to 0 here. So I see zero product property. So I find where the multiplication actually happens, which is right here where that sine x meets the parentheses, and I set each one of them equal to 0, and I have to deal with each one of them. So as my students are used to, they know that I draw a whole bunch of little tiny pictures here, and I'm going to do that a lot in this section. So I set each of the factors or pieces equal to 0, and then I deal with them separately. So sine x is equal to 0. Well, I know that sine is equal to 0 in the unit circle, and I'm thinking about the location where the y value is equal to 0, since that's sine. So that actually gives me the location at 1, 0, since that's 0, and negative 1, 0. Well, before I write that answer, I want to go over to the other one and see if there's some way to kind of wrap these guys together. So those are 2 of my solutions, and I'll come back to it in a second. Let's go ahead and solve this cosine x. So if I add the root 3 to the other side and then divide by 2, well, cosine x is equal to root 3 over 2 should look familiar. That is also one of the things from the unit circle. So we're talking about the cosine, which is the x value, being root 3 over 2, which is pretty long. So we want the x value in the unit circle to be long and positive. So I'm looking for basically a shallow triangle. These are typically, or actually not typically, but they always are my pi over 6s. So here's what I see. I see on the right-hand side, over here on my picture, I see pi over 6s, whereas on the left-hand side, I see zeros and pi's. I don't know necessarily that there's any way to wrap those things together, so let's just go ahead and write them separately. So I see x is equal to, I want to choose one of those locations, and I think I'm going to start with 0. and then I'm going to count the distance. This is a lot like when we did extrema and asymptotes and everything else. So I know that from 0 to pi here is a positive pi distance, and then back from pi to 0 is another pi distance. Because those distances are consistent, I can use that single consistent distance, and then of course I want all of them. So I use the n, just like I did back in the graphing. Now, on the cosine x is equal to root 3 over 2, I'm not sold on the distances being the same here. You'll notice that this distance is pretty short between those two, whereas the distance all the way around, that's pretty long. Those are not going to be the same. So I think I need to write these as two separate answers. So I think if I start with the first one being that pi over 6, then to get to the next one in terms of pi over 6, I'm going to have to loop all the way around. So 2 pi n. So let's put an n there. And then I still need to deal with the other one, that lower one, which is technically 11 pi over 6, or you can use negative pi over 6. I think I just want to stick in the unit circle for this. So 11 pi over 6 plus or minus 2 pi n. These three things are going to count as the solutions to this entire problem. X is equal to 0 plus or minus pi n, using pi because that is the distance between those two values. X is equal to pi over 6 plus or minus 2 pi n, because there was no consistent distance between the pi over 6 and the 11 pi over 6, and therefore I'm just using the period to try to relate these guys together. So those three statements would represent the answer to this equation. Let's move on to the next one. So in this problem I have only one trig, and there's really only one variable involved here. So I think I'm just going to try to isolate the trig itself and then evaluate the equation from there. So let's move the 1 to the other side. I don't want cosine squared, I really want cosine instead. But in order to get rid of the squared, I'm going to have to square root both sides. When I square root the left, the squareds disappear. However, when I square root the right, you cannot forget the plus or minus. You're technically getting two answers if you square root. So here I've got cosine of x is equal to plus or minus 1. So I've got a whole bunch of different solutions here. So if I want to do my cosine of x is equal to positive 1, draw my little picture. Well, when cosine of x is equal to positive 1, then that means that I want the x value equal to 1. So that's this location here. If I want cosine of x is equal to negative 1, well, then that puts me on the other end. So I'm over here. If I bring these two graphs together, so I want to see if I can kind of wrap it up somehow. So I'm going to put both of them on the same little graph together. So I've got that and that. Going back to what I did previously, I see that the distance from 0 to pi is pi, and then back from pi to the original is still that pi distance. Because those distances are the exact same value, I can wrap up my answer. So my solution is going to be x is equal to, start at one of these locations. I think I'm going to start at the the 0 here. And then you want to do plus or minus, so 0, plus or minus that consistent distance that I highlighted in blue, which is pi, and then I want all of them. So I want to put that n on it just like I did with the equations. Let's try another one. So here I have another equation, a little bit different from the last one. I have the same trig, which is good, but I have a squared and a non-squared sign. So this reminds me of a quadratic equation where I've got a squared u and a regular u on the right-hand side. In this type of a situation, I think I want this thing equal to 0. So I can try to do factoring in zero product property. So I am going to move that 3 sine x to the left-hand side so everybody's kind of in the same boat together. From here, I'm going to factor. Again, like in the previous section, if you don't see the factorization with the trig itself, you can always do U-Substitution with this. So I know that to get the 2 sine squared, I'm going to need a 2 sine x and a sine x. In order to get the 1, I'm going to need 1's here. And in order to get the negative 3, the only way I'm going to be able to get this to work is if both of these are negative signs. That multiplication of negative 1 and negative 1 guarantees the positive 1 there that I need. And then if I multiply the outside and the inside, I get a negative 2 sine x and a negative 1 sine x, which is negative 3 sine x. So I do have this factored. Now I do zero product property because it is equal to 0, so I find where that multiplication happens, and I see each one of those factors equal to 0. And then I'm going to solve those little tiny equations, draw some appropriate pictures for the unit circle that goes with them, and see if I can somehow wrap some of these answers together. So I'm going to get sine x is equal to 1/2 and sine x is equal to 1. So if I go ahead and graph those, well, sine x is equal to 1/2. Well, that means that I want the y value to be pretty small. So these are shallow looking triangles. But sine x represents y values. So I'm looking for something that is up to be positive, but really not all that steep. So those are going to be my pi over 6's. So over here, for my sine x is equal to 1, I want the y value of the point to be equal to 1, and that's this guy up here. If I were to pull these together, so I like keeping them separate first, and I'm going to pull them all together and see if there's some way I can put them into some sort of a wrapping. I don't see the same distance here. I see things that are pretty close together, and then I see things that are pretty far apart. So it looks like I'm sold there, but this is the one that ruins it for me. So that bottom portion, they're so far apart from each other, whereas the top portion, they're pretty close. But the distance is not consistent, so I think I'm just going to write separate answers for these guys. So the one on the left-hand side, sine x is equal to 1/2. I know that I'm going to have x is equal to shallow triangles, those are pi over 6's, plus or minus, there's no wrapping these up, so I'm just going to do 2 pi n, kind of whip it around the circle, bring it back to itself, and then this other one is going to be just shy of pi, so 5 pi over 6 plus or minus 2 pi n, and then this one on the right-hand side is going to give me x is equal to, well, that's at pi over 2 plus or minus, there was no consistent distance, so 2 pi n. So in this case, I'm going to have to give 3 separate answers to guarantee that I have all of them covered. So the 2 on the left in green and the one here on the right in green. Let's take a look at the next one. So this one reminds me a little bit more of example 2, where I really only have one trig. So I'm going to get the cosine squared x by itself. Oh, it looks like I'm still in green. Oh well. Move the 3 and the 4 to the other side. And then from here, I'm going to square root both sides. But remember, when you square root, if it wasn't there to begin with, you have to put the plus or minus. So as a quick reminder how we square root fractions, well, we square root the top and the bottom separately. So if I wanted the square root of 3, well, that's just the square root of 3. There's really not much I can do there. The square root of 4, though, I can. That's 2. Hopefully, plus or minus root 3 over 2 looks familiar for cosine. So I'm going to separate these. I'm going to have cosine of x is equal to root 3 over 2, my positives, and then cosine of x is equal to negative root 3 over 2, my negatives. I'm just going to go ahead and draw those pictures. So remember, with root 3 over 2, that is the longer side in a 30, 60, 90 triangle, and cosine being positive, those are x values, so I want it to be a long x value in the positive direction. So I'm looking for these shallow triangles in the positive x direction, which are going to be pi over 6's. Then, over here, with my negatives, I basically have the same situation happening. So I've got these shallow triangles, but I'm actually going to be going to the left this time. So normally what I would do is I'd try to pull these all together, but I think I'm going to pull them into two separates. I think what I can do is take that positive pi over 6 and match it up with that 7 pi over 6. Likewise, I can do my 5 pi over 6 and match it up with my 11 pi over 6. Because I have this wrapping now that goes together, I have this consistent distance, which is going to be pi in each one of them. So it gets me pi all the way around. And yes, it does take a little bit of practice. However, it is expected that you wrap up points or radians that can go together. So let's go ahead and do that. So if I wrap up this first picture, I've got my pi over 6 plus or minus that consistent distance of pi n. And on the right hand side here, I'm going to have that 5 pi over 6 plus or minus that consistent distance again of pi n. So both of these would need to be included to guarantee that you have all of your solutions. Let's take a look at the next one. So here we've moved on to something definitely a bit more complicated. We've got sine x plus 1 minus cosine x is equal to 0. There are no identities that relate sine x and cosine x. If they were squared, yes, but they're not. So there's really not much we can do here. But if we square something, maybe there is. When I do that, though, to try to get some sort of a squared relationship involved, I like to separate my trig from each other. So somebody's got to go to the other side of the equation. And it looks to me like a negative cosine x is just begging to go to the right-hand side to become positive. So let's go ahead and move him over. Now that my trig is separated from each other, it's going to be easier to square without creating some weird sine x cosine x term. I don't want to do that. I still want to keep the trig separated from each other. So I think what I'm going to do at this point is I am actually going to square each side. Now, there is a downside to this. Whenever you do this, there's a possibility that you are creating solutions that aren't true to the problem. They're called extraneous solutions. So you need to check and see if they actually apply to the original question when you're done. So if you ever square or multiply by trig that wasn't there in the first place, you have to check your solutions at the end. Otherwise, you should be fine. So let's go ahead and square this out. So sine x plus 1 squared is just sine x plus 1 times sine x plus 1. We're just going to give us sine x squared plus 2 sine x plus 1. And then the right-hand side is going to give us cosine squared x. So at this point, now I've got a mess of trig. If you think about the Pythagorean identities that we have replacements for everything that is squared. We have a cosecant squared that we could replace with a cotangent squared using the Pythagorean identity. Same thing with secant squared and tangent squared, cosine squared and sine squared. So everybody that is squared has a replacement, but people that aren't squared don't have any replacements at all. So anything that isn't squared, you're kind of married to and you got to deal with it. So the only one in here that isn't squared is that sine x, which means I need to keep the sine x, and it'd be really nice if everybody else was sines. So on the right-hand side, I am going to change this cosine squared so that it is a sine. So I'm going to use that Pythagorean identity that sine squared theta plus cosine squared theta equals 1 to try to get all of the same trig. Let's get rid of that cosine squared. So I went ahead and used my Pythagorean identity of sine squared theta plus cosine squared theta equals 1, just manipulated it a little bit. Now I've got sine squared and sine. So I'm going to do exactly what I did previously when I had a squared, a non-squared, and possibly a constant. I'm going to get everything on the same side together, set it equal to 0, and see if I can factor. So at this point I have it equal to 0, and it looks like I have a GCF of 2 sine x. So I'm going to go ahead and factor that out and then perform some zero product property. So I have my two factors now. Let's go ahead and find where that multiplication happens. Set each one of my factors equal to 0, and then solve. So the first one, I don't really need the 2, so it looks like I'm just going to have sine x is equal to 0. That s is a little small, so let's make it a little bit bigger here. Sine x is equal to 0, and then this one on the right, it looks like sine x is going to be equal to negative 1. So I find my values where sine x is equal to 0, draw my little pictures. Remember, I'm looking at the y value being 0, so that gives me what looks like 0 and pi, and then sine x is equal to negative 1, so I want the y value equal to negative 1. However, remember, in the beginning, I squared the equation to get this. So I believe, not positive, I believe that my x values are going to be equal to 0. My x value is going to be equal to pi, and then of course that whole distance as well. And my x value is going to be equal to 3 pi over 2. What I want to do is I want to do a quick check on those in the original equation. So I'm going to plug in x equals 0 first, and that's going to give me sine of 0 plus 1 minus cosine of 0. And I need to make sure that that is actually equal to 0. So I'm going to put my little question mark there. So I'm basically repeating the original equation, and I'm plugging in what I think the x values are. So sine of 0 is definitely going to be 0, as everybody knows. Bring down the plus 1, minus, and then cosine of 0. Well, cosine of 0 is definitely going to be 1. So the question is that equal to 0? Well, yeah, it is, because we get 1 minus 1. So we get 0 is equal to 0. That one checks out, which means back here where I had solved, that x equals 0 is going to work, which means I'm going to use that as one of my answers in a second. I still need to check the other two, so I'm just going to go through and do the exact same process, fill those in and see what happens. So now I'm checking the pi value. So sine of pi is 0, bring down the plus 1, and then minus cosine of pi. Well, cosine of pi is negative 1. So I'm going to get 1 minus negative 1, but as we know, those cancel, and I'm going to get 2 is equal to 0. Well, that doesn't make any sense. So this is one of those extraneous solutions I was talking about. So although we had to square, we ended up with this extra solution that doesn't make any sense. So let's get rid of that one. And then we're going to go ahead and do the same thing with the 3 pi over 2 and see if that's accurate. So I went ahead and plugged in the 3 pi over 2. Sine of 3 pi over 2 is going to be negative 1. Bring down the plus 1. Cosine of 3 pi over 2 is 0. And this one's going to work out because we are going to get the negative 1 plus 1, which is equal to 0. And we get 0 is equal to 0. So this is one of the other solutions that's going to work back here. So I'm going to have my 0 and my 3 pi over 2. Well, hopefully everybody realizes there is no consistent distance between 0 and 3 pi over 2. 0 to 3 pi over 2 is 3 pi over 2, but 3 pi over 2 back to the location of 0, which would be 2 pi, is only pi over 2. So I think we're going to have to write two solutions here. So the first one, I'm going to write x is equal to 0 plus or minus, got to do a full loop to get back to it, 2 pi n, and then the other one is going to be the 3 pi over 2 with the same situation of the 2 pi n, so plus or minus 2 pi n. Now let's take a look at the next one. Okay, so pretty basic. We just have one trig, and the idea is to get it by itself. So let's do this whole cosine of x is equal to -3. This is more of a thinking question than a doing question. We talked about this when we did arcs in class. So what we're talking about is, if I wanted to make this into a fraction, I can always put a 1 under anything I want. You're saying that cosine, as we know it, is identified as adjacent over hypotenuse. So let's go ahead and put that off to the side. So cosine is adjacent over hypotenuse. But in the problem that we have here, we're saying that the adjacent side is -3, so it would be to the left, and the hypotenuse is 1. Well, that causes some problems. There is no right triangle in existence where the hypotenuse is going to be smaller than the adjacent side. This type of a situation has no solution because cosine has to have that the adjacent side, no matter what, is always going to be less than the hypotenuse itself. So I'm not even looking at the positive or negative sign on this. I'm just looking at the absolute value of the top and the bottom. 3 is definitely larger than 1, which means you're looking for a triangle where the adjacent side is larger than the hypotenuse, and that doesn't make any sense. This has no solution. There is really nothing for us to do here. Let's move on. Okay, so we have another problem here that actually looks like kind of a mess, but I see sine squared and sine, which again is still indicating to me that I want everything on the same side. So I'm going to go ahead and subtract that 2 sine x and kind of bring everybody together. So I moved my 2 sine x from the other side, and I didn't just kind of put it at the end of the equation on the left. I wanted to try to shuffle this around a little bit so it looked like my like terms were next to each other with the whole sine x's. But I don't really want to put those together, and I can't really put them together, the 2 in the middle, because a 2 root 3 and a -2 aren't like terms, so I can't put those together. But I have 4 terms again, and having 4 terms triggers for me that I need to do factoring by grouping. So I'm going to go ahead and group the first 2 together, making sure that between the parentheses, when I do this grouping, I'm going to have a plus sign because that negative sign belongs strictly to that 2 sine x. Then from here, I'm going to try to do some Gcf factoring, and hopefully I can get the parentheses to match. So with some Gcf factoring, I am actually able to get my 2 sets of parentheses to match. This is good. So that means that each one of these is going to have that 2 sine x plus root 3 in common. Oh, and my plus sign. And then what's left over is what was left in front of the parentheses, which is what I factored out previously. So 2 sine x minus 1. And again, for this to be successful, a couple things need to happen. I need the parentheses to match, so that 2 sine x plus root 3, and I need it equal to 0. Without it equal to 0, there's really not much I can do. Now that I have a product equal to 0, I can actually set each one of those factors equal to 0 and see if I can solve from there. So let's set that first set of parentheses equal to 0 and that second set of parentheses equal to 0. Then from here, I'm going to solve for sine x in each one of those equations. So that's sine x is equal to negative root 3 over 2, and sine x is equal to a half. I'm going to take out my little pictures to represent these situations. So I've got sine x is equal to negative root 3 over 2. Well, it's negative and it's sine, so it's going to go down because that's the y value, and I need the y to be pretty large. So I'm taking a look at these pi over 3 increments. Then over here, I've got my sign being positive, so I want it to go up, and I want the sign to be pretty small. So I'm going to have these shallow triangles here. And if I tried to pull those together, I don't see a consistent distance between them, so I think I'm going to have to write out 4 answers. So over here I'm going to have x is equal to my first radian. It's going to be this guy here, and that's going to give me 4 pi over 3 plus or minus, no consistent distance, so let's do 2 pi n, just going to loop it back to itself. And the other one is going to be 5 pi over 3, the one in the fourth quadrant, plus or minus 2 pi n. That covers those two. Then to the right over here, I am going to have the one in the first quadrant right there, which is going to be pi over 6, no consistent distance, so plus or minus 2 pi n. And then the second one, which is going to be the one in the second quadrant, which is 5 pi over 6, and again, no consistent distance, so I'm just going to do plus or minus, loop it back to itself, 2 pi n. So in this case, there's no way to wrap these answers together, and I'm actually going to have to give all 4 of them. All right, our last problem for these notes is something a little tiny bit different. Major difference here is, yes, we only have one cosine, but we have what's called a multiple angle. We haven't really dealt with this yet, but you'll notice that there's no other trig in the problem. So I think what I'm going to do is I'm going to do a U-substitution here. So I'm going to let u equal to 4x. So I'm going to get rid of that multi-angle there. And I'm going to create something that I'm comfortable with. So cosine of, take out the 4x, put u in its place, and then just bring down the rest of the problem. So negative root 2 over 2. And I'm just going to draw that situation. Notice that the cosine's already by itself. I don't have to worry about doing any other work. I want negative root 2 over 2 for cosine. Cosine's the x value, and I want to go left then. And remember, negative root 2 over 2 is in the middle of a quadrant. These are the 45-degree reference angles. There's no consistent distance between those, so I'm actually going to write them out separately, but I'm going to write them out the entire answer. So I'm going to have u is equal to, so this first guy up here, and that's going to be equal to 3 pi over 4 plus or minus 2 pi n. Then I'm going to have the other one, which is next to it. U is equal to 5 pi over 4 plus or minus that distance, which is 2 pi n. Now I'm not done because I'm not solving for u. I'm trying to solve for x. So I'm going to resub back in and put my 4x's in there. So I'm going to have 4x is equal to 3 pi over 4 plus or minus 2 pi n. I'm going to do the same thing with the other one in just a second. What I need, though, is I need x, so everything is going to have to be divided by 4, so get those to cancel. So remember, dividing by 4 is the same thing as multiplying by its reciprocal, so this 3 pi over 4 is just going to turn into a 3 pi over 16, plus or minus 2 pi over 4 is the same thing as pi over 2. Don't forget to put the n upstairs. That's going to be one of my answers. Then I need to do the exact same thing over here. So I'm going to replace my u with my 4x, because again I'm solving for x. U was just a dummy variable to put in its place to help me solve. And then I'm going to go ahead and divide by 4 just like I did on the other one and clean it up. And let's see what we get. So what I have here is I went ahead and just divided both sides by 4 like I did previously with the other one. So in dividing by 4 is the same as multiplying by the reciprocal, so I get that 5 pi over 16. You want to make sure that you divide the 2 pi n also, so I get pi n over 2. So whenever we have multiple angles at this point, we'll have some others in the future, and I'll show you how to handle them a little bit differently. With these, you need to do U-substitution, or the easiest way is to do U-substitution, and then just resub back in your x at the end. If you have any questions in class, make sure that you ask.